Hi again. This is your lecture on Chapter 5. We're going to talk all about probability and the normal distribution and relate that to z-scores. So for this chapter, you will need your textbook or the tables in your textbook. Specifically, you're going to need the unit normal table, and it is at the back of the textbook, page 294 through page 296. So it's several pages of the unit normal table. I also have provided a PDF of a unit normal table that you can utilize, download and print to utilize that. You will need to have a printed copy of that, or your textbook in front of you for exams related to the tables. So let's start talking about probability, and specifically related to the normal distribution. Like if I can get this to function right, bear with me. Okay, so sorry about that. It took me a little moment. So when we talk about probability, it's just related to the likelihood a specific event will occur. So typically we'll have like some random event that we're looking for, and we want the probability that it'll be occurring again. So like if you have a die, one die, on that die there's six sides, one, two, three, four, five, and six on the die. Um, Dice is plural, die is one die, just in case you're not following me. Um, if I wanted to know what the probability of rolling the die and getting a three, then it would just be three out of six. And we would actually divide three by six to find out the probability. We can use probability to predict outcomes, and we're going to be using probability basically for the remainder of the semester. And as you can see here, probability is notated, or what they call symbolized, as a lowercase p. So bear with me here, right here, lowercase p. So if I was to do probability p equals, if I want to see how, I'm sorry, I correct myself. I said three out of six. That's not actually true. That's the number we're looking for. It would be one out of six because there's only one side of the die that has a three. So it would be one out of six. But this is not how we would report probability. And so we'll learn about why this is not how we report probability. Unfortunately, for psychological research, we don't use fractions. So let's talk about calculating the probability. So you have actually already learned this. When you learned grouped frequency distributions, you had that column that you calculated proportions. Probability and proportion are the equivalent. We often use those terms interchangeably. Probability is often used more for prediction, whereas proportion is typically what we use when we're describing something that we have, and not what we're predicting. But they are used interchangeably and really mean the same thing. So if we're looking for probability, as you can see, we need to have the total number of outcomes, so that sample size or population size, and then how often a specific event occurs. So like I said, if it was a die, three is only on one side, so that it only occurs one time, and all the total possible outcomes is six, because you could roll it and it could land on any of the six sides. So that'd be where it'd be one out of six. So if I was to write that, it would be P, and we're looking for the number three, right? Oops, I'm sorry. The number three, and there's only one number three, one X. value, and we have six sides of the die. So it would be 1 divided by 6. So 3 only occurs one time. And so we would go 1 divided by 6 to find out what the probability is. All you need is your sample size and the frequency of that specific outcome that you're looking for to be able to calculate probability at the most basic form. So let's move forward and we'll see how this is kind of utilized in a theoretical aspect. So some really, really important rules to remember about probability, and this will help you so that you're not calculating something and coming up with a number that you shouldn't be coming up with. You'll be able to catch it. And it helps conceptually if you understand these aspects. It'll help you understand if you're doing something wrong. So probability is only between 0 and 1. 0 meaning there's no probability at all. And 1 is basically equivalent to the most probable you could have, because 1, if you had the probability of 1, it's actually the equivalent to 100%, which is everything. So the closer you are to 1, the more probable an event is. So we always, always, always report probability and proportion as a decimal. So as you can see, I have that outlined right here. Always reported as a decimal or percentage. So bear with me, if I was to break my calculator out, because you don't want to do anything in your head because that's always a problem. And I'm doing the probability question from before. P equals 1 out of 6. I am going to convert that to decimal. So 1 divided by 6, you want to make sure your calculator is set to where it's providing you decimal responses and not fractional responses, because there are different settings. I am going to report this as whoops. Oh, bear with me. I am going to report this as 0.17. 0.17. That is a decimal. The reason is 0.17 and not 0.16 is because the actual number, if you put that in your calculator, is 0.166666666. We always round to the second decimal, okay? So we would take that third number, which is a 6, it's 5 or more, and so we take that and round that second decimal up. So instead of 0.16, it's 0.17. That's the probability of rolling a 3 on one die. That's really the reality of that. So either something is probable or not probable or somewhere in between. So it's only between 0 and 1. So your number is always going to be 0 to 1. It'll never be a negative number, and it'll never be greater than 1. You can't have a probability greater than 1, and you can't have a probability that's negative. So those are important things to remember, so that when you're doing calculations, you can start connecting what values are correct and what values are not correct, what aren't meaningful. So helps you to get the theoretical aspect of it. So all of this is going to be kind of applied to normal distributions. So I'm going to move my little face out of the way so we could talk about this. So the normal distribution is basically a theoretical distribution where all the scores are equally distributed around the mean. It's a symmetrical distribution where if you fold it in half, both sides are even, and the scores that are closer to the mean are more likely to occur or more probable than the scores that are far away from the mean. So as you can see on this distribution, these scores right here in this red box, those are highly likely because those are pretty much falling around the mean. They're kind of all falling within 2 standard deviations of the mean, and we'll talk about what that means. So these would be what we would consider normal. When we're doing social behavioral research, we're kind of trying to distinguish between what is normal or likely and what is unlikely. And so any of these areas like out here in the tails out here are unlikely to occur. They're less probable. So that's often what we're doing is we're using the normal distribution to find out, okay, are our samples normal, very likely, or is it an abnormal sample, or is something happening that is not probable? That's the ultimate rationale for using probability and the normal distribution. So we know that about within two standard deviations from the mean, 5% of the data will fall in those tails. So that 5% is very unusual or unlikely. So let's talk about now when we standardize a normal distribution, because truthfully, that's what we're doing is we're using a normal distribution, and then when we actually have data, we standardize that distribution and we call it the standard normal distribution. And the standard normal distribution has the scores equally distributed. It's a normal distribution, a symmetrical bell curve. And as you could see, we have it set up, where 0 is right down the middle. So in a standard normal distribution, the mean is transformed. So whatever the mean is in the raw scores, it's transformed to equal 0. And whatever the standard deviation is for the population or the sample of raw scores, whatever that standard deviation, it's transformed to equal 1. So now you can distribute these across the x-axis. Once you distribute those, you transform every raw score to z-scores. They're along the x-axis, and the z-scores really are values on that x-axis that tells us the distance in standard deviations that raw score or value is from the mean. So, and we can start looking at probabilities using that. So you can start looking at sections and saying, okay, this section has this percentage of information, this section has this percentage. So a standard normal distribution is a normal distribution that's been standardized to have a mean of 0 and a standard deviation of 1. And now the locations of raw scores are described in z-scores, is what they are. So let's kind of think about what z-scores are. So z-scores tell us where the locations of raw scores are in a distribution. So you can standardize an entire distribution, and is what happens is when you standardize your distribution, it takes different distributions and makes them able to be compared. So I can look at this distribution of IQ scores and I can compare it to a whole nother distribution of IQ scores if they're standardized. So that then there's some things that you can actually compare to one another. But it requires a normal distribution to be able to effectively compare these things. So, a couple of things to remember. Let me move my bubble head for you one more time. Okay, so there's a couple things to remember about z-scores. Now remember, probability, you cannot have negatives. Probability is different than z-scores. Z-scores are locations of raw scores when you're dealing with a standard normal distribution, which is also known as a z-distribution. You can use either way. The sign of that z-score tells you whether that score is located above the mean or below the mean. Meaning, if I have a mean of 50 and I have a raw score of 40, the z-score is going to have a negative because 40 is less than 50. If I have a mean of 50 and my raw score is 60, the sign of that z-score is going to be positive because 60 is greater than or to the right of the mean. Bear with me. The number just tells you the distance between that score and in standard deviations and the mean. So the distance from the mean to the raw score in standard deviation units is what that tells you. So those are some key things to remember. The z-scores are the only ones that can have raw scores technically could have negatives too, but when you're talking about probability and the z-distribution, z-scores can have negatives and z-scores can be greater than 1. Probabilities cannot have negatives and probabilities cannot have greater than 1. We'll talk about how those are going to interact for you. So the z-distribution, also the standard normal distribution, just they mean the same thing, has some important characteristics to remember. So the distribution has these sections that are proportions of scores, which are also considered percentages. So as you can see in this distribution that's in the top right, we have the mean value is like right down the middle, right here would be our mean, which that z-score would be 0, meaning there are 0 standard deviations. Oh, I don't know why it keeps doing that. 0 standard deviations from the mean because it is the mean. So that's 0. The amount of scores between 0 and 1 standard deviation with a z-distribution is the same for every distribution. So 34.1% of the scores will fall between 0 and 1 standard deviation. And in reality, percentage and proportion are interchangeable, remember? So that percentage, P equals, it would be P equals 0.341. That would be our probability or proportion related to this section right here, converted to probability. Percentage, remember you'd have probability if you move the decimal over 2 places to the right, that converts it to percentage. When we learned proportion, it's the same thing. If you move the decimal 2 places to the left for a percentage, that's the proportion or probability. So every proportion in those sections are the exact same on the left-hand side as they are on the right-hand side, so on the corresponding sections. So everything, if I was to take this distribution and split it like right down the middle, right here, and it's not a straight line, but it should be, all of this proportion, this entire side or percentage of this side is 50%. All of it is 50%. 50% of the scores fall above the mean. Same with this. All of this on this side is 50% of the scores. It's an exact reflection. So the proportion between 0 and a z-score of +1 is the same as the proportion between 0 and -1 for a z-score. So they're all, if you're starting to look at z-scores, all the negative means is it's below the mean, the positive is above the mean. So they're all going to be, every score can be represented by a z-score, which then can correspond to a proportion or a percentage depending upon what area of the distribution you're looking at. So some important things to remember. It's a direct reflection of each other. So to transform a raw score to a z-score, we have an actual calculation for that. So we use this z transformation equation. It's this formula to where it converts any normal distribution to have a mean of 0 and a standard deviation of 1, and then it can convert basically any of the raw scores to a z-score. So for a population, you have, see this top one here. This is the population. X is just whatever raw score you're looking for. That's a raw score. And then all you're doing is looking for its location, um, getting a z-score. So it is raw score minus the population mean, all divided by the population standard deviation to find that raw score z location. Then for the sample, it's the same thing. X, which is the raw score, minus the sample mean divided by the sample standard deviation to find the z-score for that specific raw score. So once you know that location of the z-score, you can actually use what is called the standard normal distribution to find the probability, or the unit normal distribution. And that's where the tables come in handy. So let's take a look at this. So how this would look, just at the most basic level without the tables. So let's say I have SAT scores. They are normally distributed with a population mean of 500 and a population standard deviation of 100. And let's say you obtain a SAT score of 705. That's your raw score, X equals 705. And you want to determine whether your score was at least 2 standard deviations above the mean. You would transform that equation. So you would plug in right here, 705 minus 500, all divided by 100, and your z-score is 2.05. Well, here is the minimum at a z-score 2. Yours fell at 2.05, which is to the right of that. So your score was at least 2 standard deviations above the mean. It gives you a good idea of where things fall. So that means, remember, typically within 2 standard deviations, that's kind of average, really. So that means if you fell beyond 2 standard deviations, you scored abnormally high in reality, if you were to look at it from that likely to unlikely dialogue as far as probability gives us. So we can also use the same kind of information to find a raw score. So if you have a z-score, and then you can use that to convert and find what score would fall at that. So let's say actually, I think I might have an example here. I do. So bear with me. So it's basically the same equation, except for now we just have it solving for X instead of solving for Z. So for population, it's population mean plus the Z-score times the standard deviation of the population to find its raw score at that Z location. For the sample, it's the sample mean plus that z-score times the standard deviation to find the raw score at that z location. So here's what that would look like. So again, we have the same information, SAT scores with a population mean of 500, standard deviation of 100, and you want to determine what score you would need to obtain at least 1.5 standard deviations above the mean. Now, because this says above the mean, this 1.5 is a positive. Now, if it said 1.5 standard deviations below the mean, that you would make that a negative, and that's very, very important. So we would just plug in 500 plus 1.5 times 100. Remember, multiplication comes first, so this gets done first. So you would need to score 650, and here's where your score would be located in that distribution. So now you know what you would need to score to be at 1.5 standard deviations above the mean. Kind of working it backwards. So now let's start talking about proportions related to z-scores and how we find proportions using the unit normal table. So like I said, at the back of your textbook, you have a unit normal table and several pages of this. I'm sorry, I'm sure it's not clear, but I tried to give you an example of what one looks like here. The first column, which is column A, these are z-scores. And it gives you all the possible z-scores all the way up until basically, let me find the highest z-score that it gives you. The highest z-score it gives you is 4. Now, it only shows the positives, z-scores, because remember, the proportions are exactly the same on the left-hand side of the mean as they are on the right-hand side of the mean. So if I was looking for a proportion at -1, it would be the same. I would just look up 1, and then I would have to realize it's on the left-hand side, but it would be the same thing because it's just a reflection. So in column A are your z-scores. In column B are and column B and C are proportions. So the area between the mean and z. So you have a chunk of area. The mean would be right down the middle, and maybe you're just looking for a sliver that touches the mean. That area would be the proportion between the mean and z. Column C, it is this area. Let me move my bobble head for you again. In column C, you'll notice that it's the area beyond Z in the tail. It's anything like if it's floating out in the middle and then beyond, everything beyond that point. So there's these three columns, but your normal table, if you'll notice, has three columns, but then it has like three more columns because it has like a running log. So at the bottom, let's go to this and I'll kind of talk you through it just in case. At the bottom of page 294, you'll notice that first column, the highest z-score is 0.44. Well, if you go on page 294, the fourth column over continues. Then there's z of 0.45. Actually, there's let's see, 3, 6, 9 columns. I was thinking there was only 3 or 6 columns. There's 9 columns. So it keeps running so that they can fit as many as possible. So you want to be careful. Is what I usually do is maybe use like a highlighter to separate them. And then I even draw little diagrams above each so that it reminds me. So A column is always z-scores. Those are locations. Column B and C are always proportions, very specifically proportions. So let's take a look at how this works and what we're going to do with this. So let me move myself again. Sorry. So when we want to locate proportions in these using the unit normal table. So we want to first and foremost, and this is a rule, and this is going to be a rule to where if you go out of this order or you don't complete this order, you will have points lost on your application activity and your exams. You need to draw and sketch the distribution and locate where your question is focused. That means draw a mean, shade the area that you're focusing on before you do any math, because I can tell you right now, if you don't have a visual idea of what you need, you could easily look in the wrong column on the unit normal table. So that will really help you out. So then you're going to locate the z-score that corresponds to that area that you're looking for. So that means you might need to use your z transformation formula if you're provided a raw score. Okay, so that means you'd have to transform your raw score to a z-score. Then you're going to use that z-score and find the probability in the appropriate column in that unit normal table. So we're going to go through a couple problems to practice and see what this looks like. So these steps should follow these very, very, very specific order. So if you'll notice, here's an example. We have SAT scores, and they are normally distributed. Again, the mean is 500, standard deviation is 100. An educator wants to know what proportion of students obtain an SAT score of 610 or greater. So you don't have to have exact locations. As you notice, this is just a rough sketch. So this should be done. This drawing and shading should be done before any math is done. because is what this does is this tells us once we transform this X value of 610 to a Z-score, we're going to be looking in the unit normal table in the tail, which is column C. So otherwise, you could accidentally look at column B, which would be wrong. That would be a no-no. You would not want to look there. So it helps you to navigate where you want to look. So first and foremost, that's what you should be doing. And trust me, I've done this such a long time that I can tell if you are doing the math first and then drawing after, because a lot of times is what happens is the math is driving your drawing, and that can be incorrect. So the math conceptually, if it's wrong, if you have calculated wrong, then you're drawing it wrong. If you draw it and then your math comes out wrong, you're going to know it came out wrong because it's not going to make sense according to your distribution drawing. So I can always tell if somebody's been going out of order on that. There will at least be one or two errors that will kind of trigger me to realize that the drawing didn't come first. So here's what we did to solve that. This was step 2, okay? We use that transformation equation. So we put in that score of 610 where the X should be. Population mean is 500 here. Divide that difference by 100 and we get a Z-score of 1.10. This is a positive score. Now here's where I'm saying it could go wrong. What if you accidentally swapped these two numbers and you went 500 minus 610? That would make this a negative. If you've already drawn this like this and all of a sudden you get a negative, you're going to know that doesn't make sense because it shouldn't be on the left-hand side of the distribution. It should be on the right-hand side. So it should be a positive. So this will help drive corrections, really. So your Z-score is 1.10. So step 2, now you have your Z location. You can't find proportions until you get a Z location. So we're going to use that unit normal table. And so remember, we notice, okay, this area that we were drawing is in the tail, which is column C, right? So here we are, we're going to find, first of all, first thing we're going to do is look up our Z-score of 1.10. So here's our, in column A, column A, column A, is what we're going to do is we're going to look up 1.10. So we're going to go all the way down. Here's 1.10, I have it highlighted. And now we're going to find its corresponding number in column C. So we have to skip over to this column. So our proportion is 0.1357. So our result should be reported because it's asking for a proportion. Our result is P equals 0.1337. That's our final answer. Okay. If I asked what percentage of scores fall, then you would report it as 13.37%. You would not report it as P equals 13.37 because that is wrong. Proportion is 0.1337. Percentage would be converted, and then you would drop that notation because remember, proportion can't be over 1. So here's another example. We have the SAT scores again, and an educator wants to know what proportion of students obtain an SAT score of 425 and greater. Now we're getting a little bit trickier. So 425 falls below a mean of 500. So as you could see, we have this line to the left. But this researcher wants to know what proportion of students score above that. So that means we're going to have to account for this sliver from the mean to Z, and we're going to have to add it to the other entire half of the distribution. And remember, we automatically know that an entire half of the distribution is 50%, right? We convert 50% to P equals 0.50. But now we need to find out what is the proportion between mean and z so that we can add it to it? Like, what is this proportion right here? That little sliver. So let's take a look. We have to find our z-score. If you do it right, because that 475 is below the mean, you get negative 0.75. Now, remember, step 2 is transforming. Step 3 is finding the proportion using that z-score in the unit normal table. So now we're going to take that z of 0.75. We're going to go over here and find the z-score. So if we're looking through all of the z-scores, looking. So here's the column that it's in. I highlighted it, 0.75. Now that sliver in the middle is our column B, mean to z. So that proportion is 0.2734. So is what we want to do is add 0.2734 plus the 0.50 that we already had from the other half, because that's not shown in here. You just should know that if it's an entire half, you're talking about 50% or proportion of 0.50. Add those together. So we end up with P equals 0.7734. Should be our final answer. That's the proportion. One way that you know that you're right is because when we're crossing over the mean like that, you should have more than 50% or a proportion of more than 0.50 when you're crossing over the mean and including an entire side. So we can also use z-scores and proportion to find percentile ranks. So percentile rank is the percentage of scores that fall below a specific location in a normal distribution, okay? So if a score falls below the distribution mean, that percentile rank is going to be in the lower tail. So you're going to be looking at column C for this. If the score falls above the mean, you're going to be looking at everything. So you're going to need to find this sliver, and then you're going to need to add it to the 50% below. And whenever you're asked for percentile rank, you want to report it as a percentage. Absolutely want to report it as a percentage. So let's think about, okay, so the last one, the mean was 500, standard deviation was 100, okay? So let's see if we're using that. Yeah, we are. So let's try this example out. So we have the mean of 500 and a standard deviation of 100. And a student wants to know what score they would need to obtain on the SAT to fall at the 90th percentile. So remember, all we want to do is figure out, okay, where is that located on the distribution? Well, right at the middle, right here at the mean would be the 50th percentile. Anything below this is less and less and less. So we know the 90th percentile is just going to be somewhere over here. It doesn't have to be perfect. So we could say, oh, this is the 90th percentile. So we know this is 50%. This amount right here is 40%, right? Because 50% plus 40% is 90%. So this helps us. So this is ultimately what we're trying to find is what value, what score falls there. So we've got it drawn, which is the very first thing we should do. Now is what we need to do is start kind of using the information we have to work backwards. We don't have a z-score because we have to find that z-score first. So we have all the information we need to find the z-score. As you could see, we have 50% here, we have 40% here. This area right here is column B, okay? Is what we want to do is convert 40% to a probability, which is P equals 0.40. So we want to go over into our unit normal table and find in column B 0.40, the closest thing we can find to 0.40, and then locate its corresponding z-score. The corresponding z-score is 1.29. So now you're working backwards. You're using probability or proportion to find a z. So now we know the z is 1.29, and it's a positive 1.29 because it's above the mean. If it was below the mean, we would need to put that negative in there. So now we can find the raw score, what score we would need to be in the 90th percentile. So all we do is plug and chug. 500, that's our population mean. That 100 is the population standard deviation. Now we plug in our z-score that we just found, because z of 1.29 is what the z-score that would be at the 90th percentile. And I'm sorry, my pen is doing wacky doodle things. So if we plug that all in, our raw score would need to be 629 for us to be in the 90th percentile. So it's that raw score equation, working backwards, using that raw score equation. So anytime you're asked for a probability or a proportion, you should be reporting it as P equals and then the decimal. Anytime you're asked for a percentile rank, it should be reported as a percentage. There'll be some practice activities. There's also couple of short videos for you that can help you, give you different examples of this. And please don't hesitate to reach out and ask questions if you need. Have a great day.